Well, thanks for having me here, and there's a lot to talk about in 15 minutes, so I'm just going to jump right in. What we kind of do in the space of atmospheric analytics, it's not just weather, it's not just the forecast that everybody's used to. There's a lot of information that goes into how to take data that's available to everybody and actually do something and create value out of it. So in the interest of time, the few things that I really would just like to impress upon everybody in the next 15 minutes are to touch upon the following few topics. So, everybody's familiar with getting weather data. They all see a forecast. They all understand how to retrieve weather information. What can you actually do with it? So how does weather and climate and the availability and accessibility of those pieces of information, how has that changed over the last few years? And what can we expect going forward? Now, the piece that follows that is, what can we do with that? How do smart businesses, how do smart companies, and how do smart end users create value out of that information? This weather is everywhere. This weather information is everywhere. It's become a commodity. So, the fact that it's just this ubiquitous data stream, what do we actually do with it, and how can we do something that maybe can provide us with a competitive advantage that others might not? I'll get into where we see kind of the whole space of weather and climate informatics as a science or as a collection of sciences, where that's going over the next few years. And then talk about ultimately what we're doing. CSC has this arrangement with the NASA Goddard Space Flight Center, and they're doing some really great things as far as providing basically data for everyone, putting it at their fingertips, and allowing them to take and ask the questions and do their own analyses with it. So it's a pretty exciting time in terms of how NASA is going to fit in and become this climate data service and what we can expect for the years going forward. So briefly, I just want to take a couple seconds to talk about my background. My background is in both climate physics and evolutionary biology. And a couple reasons that's important. The first is it's become very apparent recently that given the fact that I have a background in both of those fields, I'm not going to be receiving any dinner invitations for at the Texas Governor's Mansion by Rick Perry. He's publicly come out and denied climate science as well as the cornerstone of modern biology. So as far as how that information fits into end users, there still is a very significant portion of the population that doesn't necessarily understand the underlying science. But that being said, both of these sciences are, at the end of the day, they're informatics-based sciences. We have sensors, we have recording stations, we have ocean buoys, we have this global sensor network that is retrieving data every second, processing the data, putting it in a format that people can use. We have oceans, atmosphere, land, all these different types of data streams. And a lot of this, again, is available to the public. People aren't necessarily skilled as far as where the data can be retrieved, but beyond that, what can we actually do with this data? This data, for an example, is housed at NASA. Anybody can access it and start building models that we weren't able to build in the past. So what does that mean for creating value? A company like Computer Sciences Corporation is working with NASA to help build this platform, but what have companies done in the past? So I referenced before, what are smart businesses doing with this? A few years back, I used to work for these two gentlemen. Everybody says, okay, well, what do M&Ms have to do with weather and climate information? There's a very tight coupled supply chain network that started about 30 or 40 years ago. The founders of this company decided that we need to understand what the risks are for our supply chain. So if you're a company like Mars, most of your, I don't know if this pointer's working, most of your supply chain, which is cocoa, it comes from a very small slice of West Africa and a little bit out of Brazil. If something happens to that supply chain, if it's disrupted for weather reasons, disease reasons, civil unrest reasons, whatever it might be, Mars doesn't make a profit. So they had the idea, almost 4 decades ago now, to develop this research group, which evolved, not only just looking at weather, but manning a weather station, manning a network of weather stations in West Africa, which expanded kind of a global climate research program, in the effect that, cumulatively, all these pieces of information together could identify, what we kind of call weather black swans. These are events that they're not necessarily something you can forecast, but you can at least prepare against them. You never know when one of these events might come into play and, again, disrupt your supply chain. People that are in the commodity space, I used to be a commodity trader, and every day there was always something that was moving the markets that was weather-related. Probably about 7/10 of the time that was unfounded information, but nonetheless, it was information that made it to the market, prices reacted, and then we were kind of on to the next crisis. But that being said, smart companies want to take this information, put it into a package, put it into a model that can start identifying these potential disruptive events. Mars is one of the first companies to do that. Little by little, we're starting to see a little bit of a groundswell. The fact that, again, the data is becoming available to more people. They're taking a different approach to how to take weather data and do something useful with it. So the field's changed a lot. This is a map from about 300 years ago, a surprisingly accurate map when you're looking at how these wind patterns were ultimately put together, largely from ship records. But this is what the field used to be. It was just purely observational based. There wasn't a whole lot that could be done in terms of developing true predictive capability, or at least understanding where risks are, because there just was not enough data. This approach has evolved to what we know today. There's sensors everywhere, weather stations that are recording information. The difference between what I think a proactive or a smart weather risk approach is doing today versus what was done in the past, usually you're taking this information. There's a limit to what you can do with traditional. This is traditional meteorology right here. You have a variety of parameters. You put them into a model. You're solving all these differential equations for different layers in the atmosphere. You're extending once you get those results, you bring it back in your model and you keep extending it out several time steps until you have basically where too much error is introduced and the forecast is useless. Again, traditional meteorology and the limits of science, you can only really take this approach and develop something useful that goes out about 5 to 8 days. I think kind of the limits of science are saying about 2 weeks, but realistically it's about 5 or 6, between 5 and 6 days is probably where you reach that point of diminishing returns. There's too much error that's introduced and your forecast is useless. So, the alternative approach, now that we have the advent of satellites, global sensor networks, more data available at a finer spatial and temporal scale, and again, available for everybody to use. This is not privy to only government users. There's a lot of satellite information that was available, that was classified for years, that's currently publicly available and free. Cost used to be a big prohibiting factor when it came to accessing the data. A lot of this data is available now. So the fact that NASA, Goddard, and others are taking this information and putting it into a format that people can use and understanding, okay, these are the past patterns, these are kind of the teleconnections or drivers that might be leading towards a certain type of event, that's actionable. And again, the smart companies are taking this and they're, kind of with the accessibility of the data and the increase in the tools and, the ability of data analysis to, take this information and develop something useful out of it. These communities are working together now much more tightly than they were in the past. So companies can actually do something and, again, create value, not only monetary value, it can create value in terms of understanding extreme events, prevent food security issues. I mean, there are numerous subsequent offsets that we can look at this and say, okay, what can we do with this data and actually develop something of value and put it in the hands of the public? So again, this is just showing how you look at the spaghetti plots on these models. Again, this is traditional meteorology. There's a lot of variability and a lot of error associated with that approach. So the other approach that mines data, takes the data that normally wasn't looked at in certain combinations, put it in a different time series than was normally available, and there's actually something we can do with it. So a few years ago, most of what we had to do was, 9/10 of my research focused on just getting data in the format that I needed and stitching together different data sets. Just like any field in informatics, we've kind of shifted from data poor to data rich. It's still another problem, because sometimes too much data presents another set of challenges. But it's a much better problem to have than trying to stitch together these disparate data sources and develop something that you can even ask a question. The fact that we have all this data available now, we're just learning what are the right questions we should ask. So we used to get our data, have an idea, maybe test our theories against that data, and at the end of the day, there were data integrity issues, there were duration issues that we just, it always introduced a question as far as what are we actually testing. Now that we have this global sensor network that is providing this data at our fingertips, this is an example of reanalysis data that NASA provides. Again, anybody, all you need is a computer. You can log on, get the data, download the data, get a freeware image processing program, and you can construct a time series with a model, and you can test your theories against it. This leads to another approach, which is gaining popularity in climate sciences. The fact that we have these long data sets that are relatively uniform, we can do cluster analysis and network analysis. This is an example from a paper that looked into the severity of hurricanes and how that a particular year related to climatology in different years that were similar going back. So we're not going to forecast the exact track of a hurricane, but at least using this type of approach, we can take this data and say, you know what, we're going to have a year that was similar to a handful of analog years, and that's better than doing nothing. That's better than waiting until a storm develops and then basically racing to cover your exposure because either your raw material price, the market has moved on, and you're chasing the market rather than expecting this occurrence. Again, there's supply chain issues, things that are very well known. El Nino and La Nina are very commonly known, commonly accepted climate drivers. we can put those in the context of things like food prices. This is a very tightly coupled relationship between U.S. dairy production and the phase of El Nino. We can also look to extreme events. I mean, the events in Pakistan from last year, as well as the Russian heat waves that took place. Those were both issues that were very closely tied with just a little bit of advance warning using an El Nino type index. You could anticipate the susceptibility for a region for a pattern like this to develop. If you're wondering why you're paying an extra $1.50 for a 5-pound bag of sugar, a lot of that's related to how El Nino feeds into the Indian monsoon every year. For everyone in here, that probably doesn't really matter a whole lot, but if you're a sugar producer or a company that has that sugar exposure, that price exposure, this makes a difference between a profitable year and an unprofitable year. So where we are right now in the field is there's always been this interaction. You can't really be a climate scientist without having a quantitative focus to your work. And we always worked with the information-based science, but we're really starting to kind of have a meeting of the minds now. We're really starting to come together and work together and elevate the field as a whole. So if you look at what bioinformatics did years ago, they recognized that both, biology is digital. You're not going to advance the science without both of these communities working together. And in terms of informatics-based biological sciences, that's basically leapfrogged over climate sciences. But we're starting to see the same type of collaborative effort in the climate sciences. The New York Academy of Sciences held this workshop a couple weeks ago, brought both communities together. The Supercomputing 11 later this year in November, having more workshops that are dedicated to it. The primary institutions, AGU, AMS, WMO, these used to be little fringe topics that they used to talk about. There might be a session in a conference that talked about this. Now there's entire days or several off-site sessions that are focusing specifically on how can these two groups work together and what can we provide that's value to the public. New business models are going to emerge. So a company, Weather Trends, they have this a little application that you can download, and you can start to look farther ahead of the pattern and decide, okay, well, where am I going to plan my vacation? Is weather going to impact my vacation? New sensor networks, again, there's so much data that's available that cottage industries are starting to spring up around what can we, the information that is gleaned and obtained from this global sensor network. So your typical forecast, there are about 360 weather companies in the United States. All of them do basically the same thing, or most of them do basically the same thing. They provide a short-term forecast. That's a commodity. It doesn't really matter where you go. The methods that go into that forecast and the results are really not going to be very different. So what do we want to do to add value to this community? We're going to abandon what the traditional model is, which is a short-term forecast that has error after about 5 days. That makes it useless. We're going to mine patterns in historical data and focus that towards these end users that currently aren't using the information. NASA is going to be, in a few years, they're hoping to be a little different than what they're known for right now. So NASA is known for launching satellites and rockets and putting things into orbit and beyond orbit. That'll always be a portion of what they do. But they're also going to become a climate data service. They have more data just at Goddard, and more data has been made available to the public in the last year or two than the entire field has probably had access to in the previous 30 years. So instead of just looking to private services for just station weather data, we can go to NASA and ask questions and download the appropriate data that deals with all layers of the atmosphere and the oceans. It's not just weather station observations. It's everything. And this gets into the point of what is Goddard going to do in the future? They do all this stuff, but they want to do more. And this is why I think this type of forum is important, because at NASA we have a lot of data here that we want to push out to the public. Again, not a lot of people know about it, but we want to generate the data and put in a format that we're asking the right questions. We're also going to rely on companies on your side that are going to come to us with potential solutions. What is the best way for us to manage this massive archive of data? How can we put it in a format that allows a user to sit down and ask their question and have their data come to them within minutes rather than waiting a day for a model to run? These are all the things that they're thinking about. And again, they're applying to things. It's something that Tim always talks about, is to doing something that matters. One of the test studies that we're doing right now, we're taking a lot of this NASA climate data and building a malaria model. So malaria outbreaks are very tightly coupled with rainfall, puddling rates, soil infiltration, a lot of things that we derive specifically from satellites. We're not going to be able to predict exactly where an outbreak is going to occur, but if there's an area where malaria is endemic, with some advance warning, we can use these tools and techniques and say, 6 to 8 months from now, there's a certain region where malaria is prevalent, and they're more susceptible to an outbreak. There's no commercial value directly to that, but that's value for the social good. And as far as what NASA wants to do, that's a perfectly acceptable and legitimate goal. Food security is another issue. We saw the UN talk yesterday. They talked about food security. the famine early warning system is a very nicely developed network that focuses on Eastern Africa. We want to take this with the help of NASA and our partners and kind of expand this and have a food security system that alerts to potential food issues anywhere in the world. This wasn't doable a few years ago. This wasn't doable as recently as 2 years ago, but it is doable now. In the interest of time, we're just going to skip over some of the other scientific benefits of, again, applying NASA data. This is in terms of the metagenomics work that has been done in the past. We're running out of time, and I know that we didn't really leave time for questions, but at the end of the day, we're looking to develop a cottage climate industry that is taking climate data, biological data, geophysical data, geochemical data, atmospheric data, oceanic data, everything. Create new data layers, new data packages that new end users can take that data and do something useful with. Again, this is something that has not been doable in the past just due to the mindset of how weather data can be taken, played with, and developed into something useful. But right now at NASA, I'm playing with the best data sandbox in the world. There is just so much fantastic data that we have that we're pushing out there. And you can expect a lot of these applications that I'm talking about, they're not these pie-in-the-sky applications. These are real tested initiatives, and they have real end users that are going to be, again, there will be cottage industries that spring up around this that aren't your typical weather kind of company, your typical weather data provider. This is real actionable information, and we're hoping to kind of be at the ground floor of this. And with the help of everybody here, this is something that I think the industry as a whole, as we work together, we can develop these tools and really have an impact on commercial value, as well as that, again, getting back to what Tim is always talking about, doing something that matters, doing something that's good, and that people can benefit from. So I just wanted to thank everybody, Mac and Ed, for having me here, as well as Tim. It's always fun to do in a Raleigh conference because it gives me the chance to talk about my stuff in front of a different, not the straight weather crowd or not the straight climate crowd and not the straight, the commodity crowd. It's, people with different perspectives, and I'd be more than happy to talk with anybody about, any concerns or issues that you might have afterwards. And that's all the time I have. Thanks.